Okay, friends, and welcome to lecture 16 after a long time. I'm sorry for this delay, and I know this is not something which I planned actually. So, this is some unforeseen errors and some unforeseen events, especially related to the health of some of both for my kids and other people, my family members. So, this took a very long time actually, some hospitalization included. So anyway, irrespective of that, now we are back to lectures. Today I'll try to cover as much ground as possible, which we have lost in the last couple of weeks. So what we are talking about is about when we left off at lecture 15, we were looking at higher order corrections. What do they mean and why they have so much importance in understanding quantum field theories? This is a very important requirement for quantum field theories which have to describe nature. So I keep saying that they are going to describe nature and so on. So okay, and we have to see about what we are going to say about them actually. So what is that requirement? And that requirement is called renounceability. If a quantum field theory has to explain nature, it has to be renounceable, at least to a certain scale actually. Okay, forget about that, some aspects of technicality, but it should be able to describe uh, it should be able to be something called renounceable. What does renounceability mean, and what has its what are the implications? That's what we're going to do today. So let's start with the basic thing. So we started drawing Feynman diagram. So what we for various processes, but before that we have added vertices, right? So we have the vertices and the Feynman rules. Just to recap the Feynman rules of QED. So the Feynman rules of QED, essentially the interaction part contains, say, the vertex, which is given by IE gamma mu, which is electron going in. So the charge flow charge is like this. So you can also have a similar diagram for positron with the opposite line, continuous. Electric charge is flowing continuously. Then you had various other propagators like the photon propagator, the electron propagator, and so on. So these are the main set of uh, this is the propagators, and the initial and final states, like for example the photon initial state and electron initial state. Diagrammatically they are exactly the same, so I'm not really pushing anything about it. The point is that I want to let's take a process. Okay, let's take a process like E plus E minus going to mu plus mu minus, or any of this process. Okay, E plus E minus going to mu plus mu minus, right? E plus E minus going to, so E plus E or mu plus mu minus. So this is also one example we have seen. This is advantageous because it has only one diagram, so that makes life easier for us. Okay. So this would be, the diagram would be given as so if whatever, I don't know, I didn't do anything. So if the diagram, if I write the time direction in this particular fashion, this will be just E plus E minus going into mu plus mu minus. So okay, so if time is in this direction, there is only one diagram. Okay, this is the S channel diagram. Now, how did we get this process? So, we started with the process E plus E minus going into mu plus mu minus, but then so we took the initial and final states, so for this particular thing, and drew the Feynman diagram. So this is the, so let me just repeat the same thing. So what we drew was with the minimum insertion of vertices. So what did we do? We put a vertex here, and this is another vertex we have seen. Okay, so this is the minimum number of vertices we need to get these initial states and final states. Okay, but this is this, so we have to, but this is not correct actually, in the sense that this is sort of called as tree level. I'm not saying this is not correct, this is correct, but this is not complete. This is called only the first order in perturbation theory. This is just first order in perturbation theory, right? So in principle you can have okay, so this is not being seen. Okay, so this is just first order in perturbation theory. So this would mean that so this is just first order in perturbation theory. Okay, this is just first order in perturbation theory. So what it means is that you have to consider for the same set of final states, okay, for the same set of final states, all possible scenarios. So right, for example, um, so you have to consider in reality all possible insertions of the vertices in all orders of the perturbation theory with the same final states, with the same final states. So that means if you want to correct your calculation, say for example your calculation now is at the lowest, so most minimum calculation you have done. If you want, it's not the full calculation what you are doing only the basic level calculation. Now if you want to improve your calculation, say you want to go for higher order, meaning you want to, because it's just the tree level, it's only the first order in perturbation theory, and you want to compute it at a higher precision. So if you want to compute it at a higher precision, what you do, you have to take the same initial state, so the same thing, and then think of all possible diagrams which appear at higher order in perturbation theory. Let's just take second order in perturbation theory, which goes into the name one loop. So this is sort of second order in the coupling constant in alpha. We have seen that every physical process can be written in terms of alpha, alpha square, so on, so on, so. Okay, so this is just in second order in alpha. So these alpha square contributions. So what would be these contributions starting from this diagram? Because we only want those final states. Okay, we only want those final states which are interesting for us. Okay, for the example, we only want those final states which will be contributing with the same final states, which are only diagrams which would correct this particular final states. The final states are fixed. So we'll see what are the other possibilities. So if I start with say E plus E minus and mu plus mu minus, Now let's start putting vertices. So these final states are fixed for you. So now let's imagine that we are going to put all possible vertices. Anywhere else you can have some vertices. So the first set of vertices I have already drawn here, and then the second set of vertices where I can put. Okay, so the second set of vertices I can think of various ways. So let me, there will be several diagrams. This I will call it at the tree level. So the second set of vertices could be here. Say for example, at the initial state or at the final state, you can have an electron, photon is radiated and comes back to itself. So this is a vertex here, so this is a vertex here, this is a vertex here, this is a vertex here, this is a vertex here. So there are, so this is E, 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 E. So this is 4 vertices. Similarly, I could have okay, a vertex, so something like here. So I can have a vertex here, I can have a vertex here, I can have a vertex here, I can have a vertex here. Then similarly, I can have on all the 4 lines, say for example, okay. So on all the 4 lines, I can have this kind of diagrams which lead you to some sort of an photon being emitted and then getting absorbed to itself in the external line. Okay, then let's think where else you can put, but we are going to put one photon or a one electron somewhere. Okay, the only possibility is because our calculation is going to be only next order in perturbation theory. That means we can only put 2 more vertices. Here already we have used two vertices. The best we can do is we can put 2 more vertices. So let's put 2 more vertices and let's see what happens. So the other one would be, okay, maybe I'll just make it small. The other possibility would be, so instead of at the electron where it radiates a photon and comes back to itself, so we can put it at the photon itself. The photon emits an electron and then comes back to itself. Okay, so photon comes back to itself. So here also we'll have 4 vertices, 1, 2, 3, 4. So where else you'll have any other vertices you have? So here there won't be any other. Are there any other further diagrams you can think of in this direction? No. At the order of say only 2 vertices, there is no other diagrams which can correct the photon propagator. In other words, meaning which can add corrections to the photon propagator in terms of vertices. That's what I mean. Then again, this is the only thing? No, there is also one more set actually you can draw. You can take a photon from here and add it to the other line. Okay, so you can take from one of the in states and add it to the one of the out states. Similarly, from one of the in states, add it to the one of the out states. So here also you'll have, okay, 4 vertices. Okay, so minimum requirement is 2 vertices. So that gives you the tree level process. Now the next requirement is that if you include 2 more vertices into the same process, all of them give you E plus E minus going to mu plus mu minus. But these are corrections. So these are corrections. The other ones which I drew here, this bunch. This bunch have 4 vertices, but with the same process, they will be further suppressed because alpha is small. The coupling constant is small. It is a what do you call a number which is 1 by 137, right? 1 by 1. Okay. So it's a small number. So if you calculate at alpha, it gives you the dominant contribution. If you calculate at alpha square, it gives you this next small correction. Alpha cube gives you the next small correction, and so on. So now the point is that okay, I add for alpha square. Uh, uh, okay, and now this should be required. This kind of calculations are required if you have a very there are two reasons. One, you can have this kind of calculation. One, if there are processes which are only visible, which emanate only from say higher order corrections, like for example, if there is no tree level, if the tree level is 0, okay, and only from one loop these calculations happen, then these effects can be seen. In another case where these effects can be seen, if your experiment is extremely precise, if your experiment is super precise and so on, so then also this can be seen. So we are at two cases when you can see them. When these effects are important, one, tree level is equal to 0, or 2, when the tree level is 0, that means the first corrections come from at higher order corrections essentially. Okay, the first corrections come from higher order corrections. So the first effects of some process in which tree level contribution goes to 0. There are effects like that. We will give one of the examples. The other correction would be when experiments are extremely precise, we need, or the theory needs, okay, rather than saying theory needs to catch up with the experiments. Theory needs a precise prediction. In both these cases, you need an extremely you see the importance of radiative effects, meaning you can actually so these radiative corrections you will be able to see them, and then you know that the theory at the quantum level is actually there are several names for these things: radiative corrections, quantum effects, and so on. So loop calculations and number of things. So let's see the case with the first one when the tree level is 0, and another is okay, the second case essentially the tree level is 0. So in this case, what are the things which are interesting? The most important, very precise calculation where the tree level is 0 is something called the G minus 2 of the electron. The tree level calculation of this one is 0 essentially. At the tree level, the G minus 2 of the electron is the gyromagnetic ratio. Of the electron. So it tells you how the electron interacts with the say magnetic field. Okay, how the electron so this is given by the gyromagnetic ratio. At the tree level, this is 0. Okay, in QED, this will appear as a correction to the vertex. at the one loop level. Now we know that this vertex is this one, right? For example, now what is the vertex? Okay, this is just I, E, gamma mu, say for example. What is the vertex at higher order? Say for example, how do you come, how, so this is just at a tree level vertex. Okay, so this is the tree level interaction, and what does this vertex look like at higher order? So this looks like this. Okay, this looks like this. Now the vertex is replaced, plus say for example this is, so this vertex is essentially E, this is, and this one is E cube, say for example. So suddenly the coupling constant power is increased by this. So this is essentially something which is a correction of the order of E square. So this actually turns out to be, this is E plus 1 plus E square, and so on. So okay, there is an E square correction. Okay, so together these two vertices, so these two vertices will end up being together. Okay, this and this will together will end up being some corrections to this one. So what do they do? The spin of the electron, flips under the interaction with magnetic field, and how it flips tells you what is the factor in front of it. Okay, so, or rather, how it flips tells you how the what is the spin of the electron. It tells you depending upon how the what is the spin of the electron. If the spin if the spin of the electron, this is half, then its gyromagnetic ratio is 2. Okay, so this is actually covered in classical electrodynamics perhaps, and maybe other places. So what will happen is, so if you take the gyromagnetic ratio of the electron and subtract it by 0, 2, it should go to 0, and this is what happens at tree level. Okay, but due to the radiative corrections, like for example, okay, by the diagrams which I have shown you here in the previous slide, okay, by the previous diagrams, so these kind of diagrams, say for example, okay, there's additional diagrams in which there are corrections coming from higher order process. This G minus 2 will not be 0 at one loop, and further and further and further and further. So if you take higher order in perturbation theory, it will be even further, and so on. So the dominant contribution for G minus 2 would come at one loop. So this is a test of quantum radiative corrections. So where one has to compute, okay, things like this, like for the diagrams which I had to show you. Actually, these diagrams are typically complicated because these kind of diagrams are typically complicated. I'll just come to it in a second why they are complicated. So these are called quantum radiative corrections, and the first calculation of in QED QED means quantum field theory at in the present, in the way we are doing it actually, okay, was done by Schwinger. And he got the answer G minus GE minus 2 of the electron is equal to alpha by 2. In fact, this is the same even for if you take it for a muon or for any spin half particle with a charge equivalent to the charge of the electron. Okay, for any spin half particle with a charge equivalent to the charge of the electron, like electron muon tau, the first correction is just a very simple term, which is just alpha. Alpha is equal to, again I have said, e square by 4 pi, and this correction turns out to be g alpha by 2 pi, and of course you have measured this, and people experimentally it has been shown that Ge minus 2 of the electron is not equal to 0. So you mean to say you have a pretty large number, reasonably okay, Ge minus 2, which is of the order of alpha by 2 pi, not equal to 0, and it is the experiments are precise enough to show, actually precise enough to measure this quantity at an extremely high precision. Actually, I think I mentioned in one of the initial lectures that this is now known. Furthermore, it is not only it's non-zero, it is now known at 10 power at around 11 decimal places. So the precision of this experiment is mind-blowing, that you really know this one at 11 decimal places, and now you need the theory to be computed at very high precision such that you can match the experiment at 11 decimal places. So you should know your theoretical computation at a very high precision. Okay. Now what are the problems with this thing? I said that there is some issue with the computation of virtual corrections. What is this? So the virtual corrections are slightly complicated because, so let's understand why this is complicated. So let's just take one process, like we are taking vertex correction, say for example. Okay, let's just take this one. So let's just say that there is a P incoming, and now I want to compute what is the correction due to this. So I really have to assign momenta for these particles which are virtual. So here is a photon is a virtual. So this photon is a virtual particle, this photon is a virtual particle. Okay, now I have to really assign momenta for this thing. So that let's just say that there is okay, the momentum of the photon is q, okay, and then there is a momentum coming of k of the photon. This would be p minus k, okay. So this is b. So and the momentum of the external photon, I take it as negative, so that it's coming sort of coming inside. So this would be, or we okay, we can take that. So this would be p minus k plus k plus q. Okay, so this is the momenta of this line. So I am assigning momenta. Let me just maybe perhaps expand this. Can I expand this one? No, I am okay. I'm unable to expand this one, but anyway, you can see that I assigned momenta for each of these lines. So for a so this is just nothing but p minus k p minus q. This is p plus q. This is the momenta line. This would be p minus k plus q plus k. So every line is assigned a particular momentum. Now each of them is an external. Let's just imagine that this is each. So I measure the momentum of the p of the incoming electron for the photon as well as p plus q, which is not actually correct, but anyway, let's just say that each of them is sort of a real photon. So each of them is not really virtual. So let's just say that this photon is real, that electron is real, and this electron is real. So you can measure P, you can measure Q, so you get P plus Q. Say for example, let's just say, what about K? What about K? The K is some sort of an internal quantity. Okay. Now, how will you deal with K? So K is some sort of a free parameter, internal parameter, which can take any value. So which is unconstrained. So in principle, this is completely unconstrained. Okay. So this uh, okay, this is sort of completely unconstrained quantity. Okay, so it can take any value it wants. So what does it mean that if it can, so it can be minus infinity to plus infinity, so it can really take any value it wants. And in some cases this leads to divergences. So it leads to, so in principle you have to take the consideration, there is no constraint on K, there is absolutely no constraint on K, no constraint on K. So this, there is absolutely no constraint on the quantum K. So in principle, so unlike say for example in the tree level, the external momentum like P, Q, P plus Q, these are all sort of things which you have to be, which are all measured in laboratory, and so they actually have energy momentum conservation and everything. Here you're not violating energy and momentum conservation, but they don't have anything to do with the experiment and the physical process. Okay, but they still contribute to the physical process. Okay, because this part, this one, the photon in the in the vertex correction could take any momentum it wants. It can take any momentum it wants. So you have to consider all possible momenta, and when you are considering all possible momenta, it is possible that it leads to divergences in the theory. Okay, divergences in the calculations. So, uh, so what we do, so the way, say for example, okay, so this is what happens in every process. Say for example, let's just take, I'll give you the same thing, which I'll put it in, say, in a process in which there is say a plus, so for you are doing for e plus e minus going to mu plus mu minus. Okay, let's coming back to e plus e minus going to mu plus mu minus. Okay, so this is a physical process where everything is measured, but then so if you add a diagram like this is a physical process, so this should be finite and measurable. This cross section, okay, measurable. So it should be finite, meaning it should be which is finite and measurable. So when you try to compute this, Okay, when you try to compute this process in theory, it may not be finite in the sense that it could be, it could lead to some set of infinities, or so it leads to some infinities and unphysical process, like for example. So what we need, so why does these things appear? Because purely when I was computing this particular thing, uh, one second, I don't know how, okay, when I'm computing this particular diagram, because the k is unconstrained, what I have to do is, let's just compute this diagram and then you'll understand it in the physical process. Oops, what did I do? Okay, so let's just see this thing. I won't do the full calculation because it is not needed for us, because okay, we only need to know the physical principles. We won't. I'll just tell you the basic features. So, for example, we had Q coming in, P. Let's do it this way. Go okay. So this is a diagram. I wrote it in a different way. So this is P. This is P plus Q, say for example, and then let's just say this is K. This is P minus K plus Q. And this is P. This here, this is P plus Q. Okay, P plus Q minus K, and this is P plus Q. Okay, now K is unconstrained, so you just what you had to do is, when you assign all the states, say for example, so you will have an integral d power 4 K, because we have to consider all possible momenta. So this, there will be an integral for all the k's possible, because it's not constrained. You have to do an integral over all possible internal momenta, right? So similarly, you do an integral over all the possible internal momenta. In the tree level process, this internal momenta, even if there is an integral, it just is constrained by the in and out states momenta. Okay, but this is not true anymore in this particular case. So you'll have, say for example, let's do the propagator. Say so you'll have P. Say let's just do the propagator's k square. Okay, I'm just writing the factors. I'm not explicitly writing everything. So there will be a propagator for the photon, and then there will be a propagator for the electron, square, and then P plus Q minus K plus MF. This entire thing is slash by P plus Q minus K whole square minus MF square. Now this diagram, now this momentum is quite complicated actually to do it. Okay, but you can estimate whether it's divergent or not. Okay, this is the three propagators. Say for example, photon propagator, electron propagator, and another electron propagator. Okay, so Uh, okay, let me just. Okay. 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 So now you can see it better. Okay, and now you can see that there are this. Now the point is, because this goes as minus infinity to plus infinity, say for example. Okay. Okay. So you have to know what is this integral is, whether it is convergent or divergent. You need to know whether this integral is convergent or divergent. Is this integral convergent? So that's the question you have, whether it is convergent or not. If it's not convergent, then you have problems. Okay, you have problems that you have to get rid of these divergent terms in your theory essentially. Now this though it looks very complicated, let's just think that okay, this is just a vector in 4 dimensions. Okay, this integral is just a vectorial integration. Now if you look at carefully, it has some vectorial integration in 4 dimensions. So there is a d power 4k, it's like d cube of x. Okay, it's like d cube of x. Okay, times then there is a p. So this is like a x, some sort of an x. So this is like an x, and where r, okay, like an r. Okay, this is like an r, and this is also like an r. P slash is like an r. Okay, r bar or something, and k square is like mod r square. K square is mod r square. So the way we want to look at it is, this is a very simplified thing I'm saying, because I'm not going to the details, because this propagator should be very carefully evaluated in the momentum, the complex momentum space, with some prescription. Okay, so and then even this integral has to be done in very carefully in the momentum space. But it is easy to know whether this integral is divergent or not by something called power counting. It's a fancy way of calling something. So for example, I'll just neglect that this is okay. This is a Lorentz space. Say for example, I just take it as some sort of a Minkowski space. Okay, assume. Sorry, not Minkowski space. Euclidean space. Assume Euclidean space. So for example, I just say that d power 4, okay, is k is very similar to d power 4 k e. I call it as Euclidean space. Okay, very similar to, it's like a 4-dimensional vector, 4D vector. So it's like a 4D vector. So Euclidean means this is like, normally you have k0 square minus k bar square, right? In Euclidean means, so that means k0 square plus k bar square. So everything is a plus sign, so there is no distinction. So this will be like mod k square, okay, k0 square, okay. Whereas this is k mu in the Euclidean space, in Minkowski space. This is in Euclidean space. So let's just say that this is true. This is very much like that. Okay. If this is the case, then I can just use spherical polar coordinates. And then say that d power 4 k goes as, say, k power 4, okay, or k square. Okay, this goes as d power 4 k, this goes as k mod k square, k square, k square. Okay, so this goes as k power 4. So k power 4 is the length of the vector. So as k power 4. Now what about the other terms? Okay, so k is the length of the vector, right? D power 4 k is the length of it. So this is like in spherical coordinates. If you have d cube of x, we can write it in terms of d cube of x is equal to r square, so on, so angles essentially. So similarly we'll do okay, we are assuming something similar which happens also in potential. So with this assumption, so what we have is d power 4, okay, and the denominator goes as k square, okay, and the denominator goes as k square. Here the denominator goes as 1k square, 2k squares, 3k squares, okay, so k power 6. So the numerator goes as, so 1 2 2 1 2 k's, there are 2 k's, k, so d power 4 plus k plus k, so it just goes as k power 6, okay, whereas the denominator goes as again k square plus k square, k square into k square, k square into k square into k square. The denominator also goes in terms of 3k squares, so that means it just goes as k power 6. K power 6 denominator also goes as k power 6. Okay, let me just see if I can make things slightly better. Okay, so the denominator goes as k power 6. So the total integral, so let me call this integral as I of k. So this total integral I of k roughly goes as k power 6 by k power 6, that is k power 0. So this is divergent, which is called log k, goes as log k. So if you want, I can write it better. So this goes as dk k power 6 by k power, so roughly goes as, you should be more careful, just goes as d power k by k. So this integral goes as log k. Now log k is divergent, so this is a log divergent integral. So this is a log divergent. So what we have seen so far is that for the first time that there could be integral, meaning the higher order process introduce some sort of new divergences into your theory. Okay, they introduce in the calculations, they introduce divergences. So if you compute any, this is true for any physical process. Now if you put this particular vertex correction into this, so this will make the cross section, so the amplitude E plus E minus going into mu plus mu minus will be log divergent at alpha square. Okay, at alpha square, this amplitude would be log divergent. Okay, so but only taking this correction there, but we have seen that there are several other corrections, right? For example, so they also would be divergent. Okay, typically, so there are several possible divergences you can have. Say for example, this one, okay, would be typically something like quadratic divergent. Quadratic divergent means, so this would be something like dk k square divergent. So this integral, if we compute, would look like something like uh, okay, this will typically go as quadratically divergent. So if you put this as any physical process, the physical process at order alpha square would also be quadratically divergent. Okay, so if you put this in a process like, for example, e plus a minus going to b plus mu minus, like what we have been doing. So with this diagram, order alpha square would be divergent. Okay, so there will be divergences appearing here, or these divergences can be thought of as some infinities which are appearing here in computations at higher order, essentially. So there, okay, now there is a systematic process of isolating the infinities and removing them. The process of isolating the infinities in, these are called loop integrals. These are all integrals which are called loop integrals. It doesn't matter whether they are quadratic divergent or some other, but there are some divergences which are coming. This is because of some infinities sitting here, because the k goes to any infinite value, right, essentially. So this isolating the infinities in loop integrals, these are called loop integrals, is called regularization. So this is called a regularization of the integral. So you can actually isolate. I won't go into the detail. There is several regularization methods. Okay, you can remove them by something like by something called that. There is something the most popular of them is called the dimensional regularization, which is a completely different ball game into itself, which I won't. It will take a lecture on its own, but I won't go into the detail. The other thing is called Polyvirus Regularization, which is essentially introducing a cutoff, okay, or some massive fermions to regulate this particular integral, essentially. Okay, and so this all these integrals are these infinities are isolated. Okay, these are isolated, and these are these infinities. Now you can say, now what you can say is that if there are some physical what are the parameters in your theory. Say for example, let's just take the parameters. Then the next process of isolation is called something called the renormalization. The isolated infinities through regularization are absorbed into the physical, let me just use this word, physical parameters of the theory. Are absorbed into the physical parameters of the theory. So what are the physical parameters of the theory? Say for example, in this particular case, okay, so say for example, let's look at the wave function. of QD, LQD. Okay, so the physical parameters of this theory are one second, why this stop broadcast testing? Yeah. Um, the isolated infinities, so we isolate all these infinities to a process called regularization. Say, for example, for each diagram or vary of this particular thing, and then we ask the question that what will you do with these isolated infinities? You just throw them away, or what do you do that? Okay, so you cannot just throw them away because it's not correct actually. So you have to absorb them into something called the physical parameters of the theory. So what are the physical parameters of the theory? You have to absorb them in terms of some physical parameters, in the sense that, so if you just take the LQD, say for example L, so there are the wave function psi bar I del slash minus m minus 1 by 4 f mu nu f mu nu. So what are the physical parameters of the theory? What are the things which are important in this? So then there is a coupling constant E, mass of the electron, the coupling of the electron, the wave function of the electron, and the photon wave function. Okay. So what you do is you say that you should know how many infinities are there in your theory. How many kinds of infinities are there in your theory. Now, this is a very tricky question, because uh, how will you know? Because how many diagrams you are going to calculate? So, for each set of diagrams which we have seen, so there could be large number of infinities, right? For example, so we said for each higher order process, there could be large number of infinities. Say, for example, this infinity could be different from this infinity, this infinity could be different from this infinity, and so on, so on, so. Now, how many infinities are you going to absorb? You only have 4 parameters. Say, for example, the wave function of the electron, the wave function of the photon, and electric charge, and the mass of the electron. That's it. There is no other parameter in the theory. Okay. So this is an issue for us, right? For example, how will you know what it is? But there is then an organizing principle. Actually, there is actually a nice, very organizing principle, which I said several times. So it turns out, well, this is a non-trivial result in QD, okay, that there are only 3 kinds of infinities in QD. Only 3 kinds of infinities. Only 3 kinds of infinities or divergences in QD. Okay, there are only 3. So this is what I have been harping in the lecture 15 also, actually, that there are only 3 kinds, and this is a very big result actually. So the organizing principle tells you, okay, so if you absorb the infinities in these 3, then you can, in any process, in any physical process, the infinities at order alpha square are completely gone. Okay, this is an important statement. This is okay. that if you absorb the three kinds of infinities, if these three infinities, there are enough number of parameters in your theory, then the infinities in all possible what do you call in all possible physical processes are not there. Okay, they are gone actually. So what are these three what do you call the three organizing ranges? So one is called self energy, which is just this diagram where there is an electron line and then there's a photon correction P. Okay, this will be Q. Okay, this will be P minus Q and then P. Okay, that's it. P goes to P. The other is vacuum polarization. Again, this is this. This is the other diagram. So, which this set of diagrams which you already seen. This we have put it for the external lines in the previous diagrams. Say for example, in E plus E minus going to mu plus mu minus. So, this is the class of diagrams. So, if when I drew this set of diagrams, so this top row is the one of self energies. The second row is the vacuum polarization diagrams, and the third one, okay, is the one which we say as vertex correction. So this is the diagrams of this type. And there is a diagram, so there is a correction coming from here. Okay, so these three diagrams, somehow if I absorb these three infinities from coming from these three diagrams into these parameters, now you have only three infinities, okay, and four parameters. So the system is over constrained actually. Okay, so there are four parameters. Okay, where is this here? So this E, M, psi, and mu. There are four parameters and three infinities. The system is over constrained. So if you absorb this thing, so the three infinities by defining new E's. So for example, so E goes to E. E goes to something called some Z E. Let's just start with psi. Psi goes to some Z1 psi. So then A goes to, this is not really required, some Z primes A. So this is not required because you only need three renormalizations, right? Okay, let's just say that. And then E goes to, I am using two kinds of notations. Let me not use this psi plus delta psi. Delta psi, E goes to E plus delta E, M goes to M plus delta M, where delta psi could be an infinity and psi could be something called the bare. These are called bare quantities. Okay, these are all bare quantities. M, electric charge, and all that. These are your infinities. Say for example, the E, deltas, and everything. These are all the infinities which are isolated in these diagrams. So you isolate the infinities and the finite parts are added to this correction, say for example. So the red parts are your infinities. Now these are added in such a way that this psi, you will have all of them to be physical. So physical quantities. Okay, so you add this you shift, this is called this process is called renounceability. So you shift your all the physical, the wave function, the electric charge and the mass of the electron by so you say what your what or if you want the original terms in which appear in the tree level of the Lagrangian are something called the bare Lagrangians, bare parameters, which could contain which are sort of not the physical things which you measure, okay, but these infinities which you absorb them and put them together, they end up, okay, they end up absorbing these infinities and together they become something called physical parameters. But this what happens is at this end of this process, these physical parameters become something called momentum dependent. So the physical is something which is dependent upon the momentum of probing. Okay, electron physical electric charge also becomes q square dependent, mass become q square dependent. So this where q square is the energy of the experiment. So essentially energy of the experiment, so the physical quantity, so if you are doing an experiment at a q square, so your mass, energy, everything become dependent upon the in fact your wave function, in fact all of them should be dependent upon what energy your experiment is happening. Now uh, I know this is uh, sort of it looks like a wishy-washy. So you say that okay, this delta psi, delta E, delta M, it's like a renormalizing. So you just absorb. These are essentially some infinite quantities. You know, you isolated these infinite quantities, and you express them as delta psi, delta E. These are also sometimes called as counter terms. And then you say that your physical quantities are just that you take this, add these two in the Lagrangian, and and when you do this you get your physical quantities out of it. So you add these counter terms, it removes all the infinities. Okay, these counter terms will remove all the infinity, or this delta psi plus psi, if you put it in the Lagrangian, will remove all the infinities and gives you the physical quantities like the wave function, the electric charge, and mass of this particle. Now this looks, so this is some sort of an algebraic trick you are doing. So it looks like that. Okay, it looks like you are doing a algebraic trick, but there is a physical explanation behind this. We'll come to that in a second. But just I wanted to make one comment here, essentially that we could in QED could isolate the kinds of infinities you can have. Okay, we could isolate the kinds of infinities. I said there are only three kinds of infinities, and then you could say that these are the four parameters. So you can absorb these three kinds of infinities into this four parameter. So the theory becomes so physical. So the theory is measurable. There are no infinite quantities at any order in perturbation theory in QED. So the theory of QED is renounceable at all orders in perturbation theory. Okay, it turns out that there is a very big analysis, quantum field theory analysis, which was shown that the theory of quantum electrodynamics is renormalizable at all orders in perturbation theory. So this is okay, much more complicated, very strong statement, which tells you that you can measure or you can test QED at every order in perturbation theory. You can really compute at infinite order in perturbation theory in QED. Essentially, order by order, you can compute. There will be infinities. These infinities can be absorbed by the procedure by redefining your fields. Like for example, you redefine your parameter psi physics, all the parameters like psi, e, m, a. All these parameters can be redefined because there are enough number of parameters compared to kind of infinities in your theory, and such a theory is called renounceable theories. It's very important. Okay, it's a very important quantity, a very important quality of a quantum field theory, which is required if you want to test your quantum field theory with experiments. So if you want to test your quantum field theory with experiments, it has to be renounceable. If it is not renounceable, there is no way you can test it, because you will have all these infinities floating around actually. Okay. So QED is a renounceable theory, so you can test it at all orders in magnitude, or orders in perturbation theory. Okay. Now this entire thing of renounceability looks like some sort of redefining all your parameters. So you redefine your field. So you say that okay, this psi, I redefine it as psi plus delta psi, and this E, I define it as E plus delta E, and M, I define it as M plus delta M, and so that complete infinity goes away from your Lagrangian, and so it gives you that psi physical, E physical, and M physical. That's what you're doing essentially. So okay, now that's what you're doing. So, is there any physical thing what you're going to see? Meaning, in this process, essentially, is there any physical reason why this works? Essentially, this entire thing about. So, this is what we'll see now. Okay, let's just look at the example of electric charge. What this process of renounceability tells you that, let's just say that there is an electric charge, bare electric charge. So, this entire renounceability tells you what's happening of this electric charge. Now, if you want to test this electric charge, so this is an electron sitting here, you'll bring another electron somewhere from somewhere. So, this is a test charge. Now, this test charge has some momentum q. So, if it is sitting at rest, it sees some nothing. Essentially, it sees the a very. So, but this electric charge is not really stable. No? I mean, it's not just sitting there. For a small infinite decimal time periods, what does it do? It starts producing a photon. Say, for example, electron will produce a photon, and this photon reabsorbs itself. And so, what it does, it starts covering itself with photons, and these photons will have electron positron pairs. So, these electron positron pairs, because this is an electric E minus sitting here, E minus, so they will realign themselves. So, they will realign themselves such that the positive charge is towards the negative charge. So, they attract it, right. So, and there will be a small shift of this electron towards the other side. So, these things will be start building it up. Essentially, there could be lot of pairs of electron positron which are built at very tiny fractions of time. Okay, there will be a very small period of time, and they will be there, and they will realign themselves such that the positivity of this electric charge goes towards uh, the negative electric charge, the original charge which is negative. So, this is a negative electric charge sitting here at the bottom, and that will be sort of. So, now this now this, what it will see, what this test charge will see is an total effective charge. So this test charge will see an effective charge of this bare charge, this red dot, the original electron, times all this electron positron pair sitting here, and then because the positive charge is reducing this electron negativity of the electric charge, okay, the positive charge will start reducing this negative electric charge. So they will see an effective charge which will be much less than the original electric charge. Say for example, if there is a electric charge of some units, say delta, so negative charge delta E negative, it will be reduced by small delta, okay, of E plus, okay, positive charges, such that the total thing would be some sort of an E effective. This is what the effective charge which this test charge will start saying. Now, if the test charge attains some momentum, say for example, if it starts has some momentum, say for example, this effective charge will be very low. So it will be, compared to the original bare charge, it will be very low. So okay. Now, if the test charge attains some momentum, say for example, it starts having some momentum, say a red line, some momentum q, say for example, some momentum, or say k, some momentum k, and then it starts probing this electron cloud. So what it will do, it will require more and more energy to probe this cloud deeper and deeper. So as it probes deeper and deeper, it goes deeper inside the cloud, and this part will start reducing. With higher and higher momenta, this will start the effective charge, this vacuum polarization clouds. Say for example, this clouds of E plus E minus pairs which are sitting there, and all of the E pluses focusing towards the bare electric charge will start, penetrating this cloud, and it starts penetrating this cloud, and it goes deeper and deeper. So this cloud effect will be reducing. So this valve will start seeing the electric charge is not to be the small thing which it saw earlier when at zero momentum, but it will start seeing it to be something larger and larger and larger. Okay, it starts seeing something larger and larger. So now if you probe deeper, the entire idea of renormalization is that if you probe deeper, completely deep inside, okay, at infinite momenta, that would require infinite, you will actually see at a very large momenta, so it's not really infinite momenta, but it will be far more than the Planck moment. So you'll actually see the electric charge to be sort of infinite. Okay, if you really probe deep inside and sit on the electric charge there, the bare charge, you'll actually see it to be electric. Okay, all this sounds very nice and good and everything. Is it actually measured? Meaning it's actually what happens in experiments. So in experiments, so what it means that, okay, so it all depends upon what the electric charge. So the summary is that if at least this entire theory tells you that if you measure electric charge at one scale, at a momentum scale, and if you measure it at another momentum scale, the electric charge should change. So it modifies itself essentially. It actually should increase. So is this measured at exponents? Yes, it does. So at atomic scales, say for example at alpha, which is equal to E square by 4 pi, at atomic scales, say for example Q squares around MeV or something, which is a very small scales at energies around MeV, is 1 by 137, what we see actually. And the same alpha at E square by 4 pi, again the same thing, but Q square is equal to hundreds of GeV square goes as 1 by 128. Okay, at energy scales, say for example at colliders. So this was what was measured at the collider called LEP. Okay, at Cern. So the LEP collider at Cern, okay, what it was is an collider has essentially, it's a collider of again the same radius as LHC, about 27 kilometers LHC, which had electrons and positrons going in opposite directions. This ran up to 2002, I think. Say for example, 1990s to 2002. Say for example, around this period essentially. This has electrons and positrons going in opposite directions with the momentum of these electrons q square around 100 GeV square. And q square of the electrons also about 100 GeV square. So these were both accelerated at energies around 100 GeV square, electrons and positrons, and collided at 4 different points. At 4 different points, and then you actually check what is you get an information, you manage to get the information at what the electric charge at those energy scales is, okay, and it turned out to be q square and alpha, okay, it actually increased. So this is the data point and this is another data point. It's very precisely measured. So this is LEP. There are other experiments, say for atomic scales. Okay, so this was really measured. Okay, if this is some, this is essentially this red dot, essentially some sort of an indication of the data. So this tells you that the alpha varies with energy. First of all, varies with energy and further increases with energy. Okay, so this is the importance. This is the importance of renounceability and higher order corrections in quantum field theories, and in particular the case of quantum electrodynamics. Okay, so what we have learned today is that higher order corrections in QED are extremely important. Okay, and the theory of QED is renounceable. Okay, it's a renounceable theory because it can, it has enough number of parameters to absorb the infinities generated at higher order. Okay, higher order corrections, and these higher order corrections are extremely important. Like for example, for to match results with experiments, like for example in the case of say G minus 2 of the electron, and say for example in the case of LEP, it is essentially E plus E minus. Okay, this is the cross section of where you measure the E plus E minus cross section to for example various other f bar and So there is something called the forward backward scattering and so and so. Essentially you can measure these cross sections at a very high precision and then dig out the information about how the electric charge transforms or modifies with energy, and you can actually check that it gets modified with energy. And this has been verified by experiments. This is a very important property of all the quantum field theories, which have to explain interactions, in particular uh, interactions like electrodynamics or quantum chromodynamics, meaning what you call strong interactions, and then there is something called the weak interactions. So in the next class, I'll revise a little bit about group theory. Okay, this is a modification compared to the previous the schedule I gave you. So before entering strong interactions, what I'll do is I'll just do some elements of group theory in the next 2-3 lectures. Okay, and then I'll come into strong interactions. So what we have just so far covered in this last 4-5 lectures is essentially the electrodynamic interactions. We know how to compute them. We can compute the electromagnetic process. Okay, and in the full relativistic regime, we have looked at some important experimental results, like for example, E plus E minus going to me plus me minus. We have seen the Feynman diagrams. Okay, and we have seen something called the G minus 2 of the electron. There is some there is something called if you do it for the muon also, there are other issues, like for example, the theory doesn't match with the experiment which I mentioned. So that's a very challenging thing, which is very interesting. And then we said that the QED is renounceable. In today's lecture, we looked at QED's renounceable theory. Okay, and so you can compute it at very high precision in your theory, and 99 okay, I shouldn't say anything, but okay, almost all known except for the G minus 2 of the muon. It may not be the QED may not be the reason for it. Okay, except for the G minus 2 of them. All the experimental results, I just showed you one experimental result from LEP, but all the experimental results match with QED so well that it is called the jewel of the quantum field theory. Okay, jewel of quantum. So with this, we'll stop this lecture today, and then we'll come to elements of group theory starting from the next lecture.